Hi everyone. So in the previous video we saw MOS as a current source. When we are using MOS in the saturation region, it acts as a current source with some output impedance, right? This is what we have seen. Now what is the issue with the MOSFET when we are using it as a current source? So what is the issue? That we will see. So there will be a current I. If the MOS is acting in a saturation region, there will be a current I. So what that current I would be? That would be mu n Cux W by 2L VGS. What is VGS? That is VP minus Vt whole square. How will you make this VB? If you have only one supply, if you have only VDD supply, how will you make this VB? By potential divider, right? By potential divider, you will be making this VB. This is R1, this is R2, and this will be your VB. So VB would be R2 upon R2 plus R1 into VDD. So this will be your VB. So basically your I would have been mu n Cux W by 2L R2 upon R2 plus R1 into VDD minus Vt whole square. What do you see here? Now this Vt is depending on temperature dependent. This Vt threshold voltage, this depends on temperature. This mu n, this is also temperature dependent. This Vb voltage, bias voltage, this is supply dependent. Supply dependent. This was temperature dependent. Right? This is also temperature dependent. So what do you observe here? You observe that this Vt, mu and Vdd, this is supply dependent. So all these are temperature dependent. So this I is not constant with respect to temperature. With respect to change in the supply, it can change. The thing is, in a chip, let's assume you design a chip and there is a Vdd supply. So this supply is also not constant. Let's assume if my supply is 1 volt, sometimes it can change to 1.1 volt and sometimes it can change to 0.9 volt. This you will learn when you go into industry. When you see a chip, the supply can change. So this current will not be constant. So here what we get to know is that this I is not constant. So that is the issue. When you use MOSFET as a current source, this I is not constant. So this is the conclusion. So we actually need a constant current source. And for making that constant current source, we use a circuit that is known as band gap circuit. So for making a current source which is independent of supply and temperature variation, we need to use band gap circuit. Now this band gap circuit is out of the scope of this course. Out of the scope of this course. That means in the gate exam, it will never be asked. Band gap circuit is not useful for your gate examination. It is not mentioned in the syllabus. Even in the interview, they do not ask it. If you are someone who is doing M.tech and you have mentioned some project using band gap circuit in your CV, then only they can ask you question on band gap. Otherwise, they are not going to ask you question on band gap reference circuit. So if you have a project mentioned, then you can expect some question. Talking about the placement course, in the end I will teach you band gap reference circuit. But for the gate aspirants, I am not going to teach band gap reference circuit, band gap circuit. Okay. So you just need to know that by using a band gap circuit, we can get a constant current source which is independent of supply variation and the temperature variation. And that current source is known as golden current source. Golden current source. That is constant current source, basically. Constant current source. So we get a constant current source from this BGR circuit, from band gap reference circuit, from band gap circuit. We get a constant current source. Now you have that current source with you. Now you have a constant current source with you. Now using that current source, you have a constant current source. You have a golden current source. I golden. I golden, or sometimes we call it I reference. You have that reference current source. Now using that current source, you need to make more current sources. This is your target. And for that we use current mirror circuit. You already have a current source. By using that current source, you need to make more current sources, which is identical to this IREF or this I golden. So from band gap circuit, you will make a constant current source, and by using that current source, you will make copy of those current sources that will be identical to this IREF. So for that we use current mirror circuit. So with the help of golden current source, we will generate other current sources which are identical to the current golden current source or reference current source. So basically, you will already have a golden current source. This is the golden current source you are having. By using this current source in a circuit, this is a circuit. This is a particular circuit. This is a particular circuit. By using this current source, you will make copy of other current sources. You will make copy of the current sources. I copy 1, I copy 2, and this, let's call this as I ref. So this I copy 1 will be proportional to I ref. So if I ref is temperature independent, if I ref doesn't change with respect to temperature variation or supply variation, then this I copy will also not change. If this I copy 2 will also not change, because this is also proportional to I ref. So for that we need to use current mirror circuit, but we directly will not use current mirror circuit. What we need to do, we have a golden current source, okay, and from that we need to generate an output current that should be independent of the supply and everything. You have a golden current source. With the help of that, you need to generate a I copy 1 and I copy 2, and that should be independent of supply variation or temperature variation. So we will try making the circuit. First, what we are going to do, we are going to use a resistor. We are going to use a resistor. So what I am going to do, I have a golden current source, or I have a reference current source. I will use a resistor now. What I will do, I will use a resistor R. I am calling this reference current source as I naught. Okay. So I am going to use a resistance R. Now this current is flowing through the resistance R. So what voltage drop it will give here? I naught into R. Now this I naught into R voltage drop will be fed to the MOSFET. Now this voltage drop is fed to the MOSFET, and from there we are generating some current. There will be some other particular circuitry here. Let's not make the circuitry, and we will make sure that this MOS is working in saturation region. MOS in saturation region. Let's call this node as V naught. So adjust V naught such that MOS is working in saturation. So till now what we have studied, we have already generated a constant current source. We are passing it through a resistance R. With the help of this voltage drop, we are giving it to a MOS, and now this voltage drop that is here, that is I naught R. Now this voltage drop will generate some current that we can call I copy. So let's check out what is the equation of I copy. What will be the equation of I copy? That would be mu n cox W by 12. What is your VGS? VGS is I naught R minus VT. Now this current is not depending on the supply. This is your VDD. So this current is this current I copy. This doesn't depend on supply. So if there is variation in supply, still the current will be constant. If there is some variation in the supply, still the current will be constant. Why so? Because this current is not depending on the supply, but this current is depending on mu n and Vt. Both are temperature dependent. Temperature dependent. Both are temperature dependent. So that is the issue here. We try to make a current source, we try to make a copy of this current source which should be independent of the temperature variation. But this is not the independent of the temperature variation, it is depending on the temperature. So this is not a good idea. So what we will do now? We will use diode connected transistor. What we will use? Diode connected transistor. Have you studied about it? Yes. In the common source amplifier, I told you about diode connected transistor. So how does the diode connected transistor look like? This is a diode connected transistor. Okay. So I will make it properly. So what I will do? I will pass the current. I will pass the current which I was having, which is I naught. So I will pass this current from a diode connected transistor. Passing the current from a diode connected transistor, that will generate some voltage V. Are you getting this point? And then this voltage V, I will be giving it to some MOS. This voltage V will be fed to some MOS. This I am going to do. So let's find out what is that voltage V. So what is this I naught? This I naught will be flowing here because there will be no current coming here, right? There will be no current coming in this path and there will be no current here as well. So there is zero current here. So what? Let's find out the voltage V. So what that voltage V would be? So what is I naught? I naught is equal to mu n cox W by 2L. VGS, what is VGS? VGS is V minus VT whole square. So what is your V? V is under root 2L by mu n cox W, 2L by mu n cox W into I naught plus VT. Well and good. 12 I naught plus VT. This is V. Now this V is fed to some other MOS that we are going to connect here. This V is fed to some other MOS. There will be some particular circuitry there. Let's not talk about it. So now here there will be I copy and we have to adjust V naught. By using some circuitry here, we will adjust V naught such that let's call this one as M1. Okay, this one as M2. So this W by L would be of M1. We will replace it. This W by L would be of M1. This W by L would be M2. So here the W by L is W by L of M1 and here the W by L is W by L of M2. Right? So I guess I should change those equations because I need to write W by L of M1. So what will be your I naught? I naught would be mu n cox W by L of M1 divided by 2 VGS minus VT whole square. So what will be V? V will be 2 I naught upon mu n cox W by L of M1 under root plus Vt. This is the equation 1 and this voltage is fed to this M2 and you have adjusted V naught such that M2 is working in saturation region. Now if M2 is working in saturation region, then what will be the equation of I copy? I copy would be mu n cox W by L of M2 by 2 into V minus Vt whole square. What is V? This is V minus Vt whole square. So that would be equals to mu n cox by 2 W by L of M2. What is V? V is this root 2 I naught mu n cox W by L, root 2 I naught mu n cox W by L of M1 plus Vt minus Vt whole square, right? This was your V. I replaced V here, nothing else. Vt will be get cancelled, and this root will be cancelled by square. So what you are getting? This mu n cux will be cancelled. 2 and 2 will be cancelled. So what do you get? So this I copy would be simply equals to W by L of M2 divided by W by L of M1 into I naught. That's it. This is your I copy. So here the current is independent of the supply variation, also the temperature variation, because the current is neither depending on mu n, neither it is depending on Vt, nor it is depending on Vdd. Are you getting this point? Neither on supply, neither on temperature. So this I is independent of independent of supply and temperature variation. So no matter if supply changes, variation. If supply changes or temperature changes, the current will be constant, and that will be proportional to I naught. So this was our target, to produce a current which is proportional to the golden current source, and that we have done using two MOS transistor. One was diode connected load, and the other was you made sure that M2 is working in saturation region. So this particular configuration is known as current mirror circuit. Okay, so let's write down the conclusion of the current mirror circuit, or better I should write the conclusion here only. So we are doing the alternative analysis of current mirror circuit. So let's just assume this is V naught. Now this is current mirror circuit only when both M1 and M2 are in saturation region. M1 is certainly in saturation region. Why so? Because drain and gate are shorted. If drain and gate are shorted, that means it is certainly working in saturation region. We have to make sure that M2 is also working in saturation region. M2 is also working in saturation region. How you will make sure? By adjusting VDD and R. By adjusting VDD and R, you can make sure that it is working in saturation region. Because if you adjust VDD and R, V0 will be adjusted. So you have to keep V0 such that your M2 is working in saturation region. So what is the condition? What is the condition for current mirror? Both M1 and M2 are working in saturation region. Both M1 and M2 are in saturation. This is the major condition, that both should be working in saturation region. If one of them is in linear, then the situation will be different. Well and good. So write down the I naught equation. That would be mu n cux W by L of M1 VGS minus VT. Let's assume this is V. Both have same VGS. This has VGS equals to V. Here also VGS equals to V. So VGS of M1 should be equals to VGS of M2. That is equals to V. Say yes or no, right? Mu n select W by L, VGS minus VT whole square. What will be your I out? This is your I naught. What will be your I out? This is the I out. What that will be? That will also be mu n cux W by L of M2. VGS, what is VGS? V minus VT whole square. Let's call this as equation 1, this as equation 2. So equation 2 divided by equation 1. What do you get? Equation 2 divided by equation 1. I out by I naught. That would be equals to W by L of M2 divided by W by L of M1. So from here, what do you get to know? That your I naught is equals to W by L of M2 divided by W by L of M1 into I naught. That's it. So the current that is copied, that depends on that W by L ratio only. That's it. Let's see a simple example, very simple example we can see. I will add up a page. Very straightforward, very simple example. I will just frame it here only. Let's call this as VDD. VDD is, I am assuming it to be 5 volt. VDD is 5 volt. This resistance R is 2 ohm. Then there is this diode connected transistor. Then there is this another transistor. Okay, there will be some circuitry ahead, and this is your, forget about it, no V not nothing. W by L of this, if this has W by L, this has 2 into W by L, and this is your I out. This potential is given, that is equals to 1 volt. And also what is given? It is given that both transistors are working in saturation region. This is given. Find I out. This is the question. Find I out. So what will be I out? I out would be W by L of transistor itself. Okay, forget that. First find the current here. If this is 1 volt, if this is 0, this will be 1 volt. So this will also be 1 volt. So what is the current here? That is 4 ampere. Sorry, 4 by 2, 2 ampere. Now is there any current here? No. 0 ampere current here, 0 ampere current here. So there will be 0 ampere current here. So the complete 2 ampere current is flowing through this transistor. So this is the 2 ampere current that is flowing. So in the transistor, if 2 ampere current is there, what will be the current here? That would be 2 into W by L of this transistor divided by W by L into 2 ampere. So I out would be 4 ampere. That's it. You just need to go by the W by L ratio. 2 ampere current is flowing. If the W by L is doubled, current will be doubled. If 2 ampere current is there, if W by L is tripled, then the current will be tripled. If W by L is half, the current will be half. 2 ampere, half, 1 ampere. 2 ampere double, 4 ampere. 2 ampere triple, 6 ampere. Are you getting this point? That's it. 2 ampere current is here, it will be doubled. But make sure both the transistors are working in saturation region. That is the most important point. Both should be working in saturation region. That's it. That was the complete analysis. Let's move on to our next topic, that is current mirror circuit but using PMOS. Same, that's it. This is the current mirror circuit using PMOS. So here, this is the current that is flowing through M1. I naught current is flowing through M1. And what will be I out? So I out would be equals to W by L of M2 divided by W by L of M1 into I naught. So this will be your I out. That's it. Are you getting this point? So this is the concept of current mirror circuit. Well and good. Let's solve a question. So both transistors are perfectly matched. This is given. Both transistors are perfectly matched. What do you mean by perfectly matched? That means they are having same W by L. Same W by L. W by L is 10 for both of them. You need to find the value of R to get 100 microampere output current. So it is given that output current is 100 microampere. If both are having the same W by L, that means what is the current here? Tell me. Look, both transistors are perfectly matched. Okay, it should be written that V naught is adjusted such that, okay, it is not given. Okay, what is the lowest possible value of V naught? This is what they are saying. What is the lowest possible value of V naught such that this transistor M2 is working in saturation region? The question is incomplete. I should have such that M2 is working in saturation region. So M2 is working in saturation region. This is working in saturation region. This is also working in saturation region. That means both are in current mirror and both are matched. That means if 100 microampere current is there, this will also have 100 microampere current. So in the transistor M1, I know there is 100 microampere current. Well and good. There is 100 microampere current. What else is given? Vt value is given, mu n so x wyl value is given. So mu n so x wyl value I am having. I don't have the VGS value. So first I will find the VGS value, this potential V. First I will find the potential of V. So what I can see here is that 100 microampere current is equals to mu n so x is 200 micro into WL is 10, right? WL is 10. VGS by 2. What is VGS? VGS is V minus VT is 0.7 whole square. So you can solve this equation. It will be V minus 0.7, that is equals to under root 10. Under root 10 is nearly 0.3, 0.314 near around that. So V will be nearly 1 volt. So V value you are getting is nearly 1 volt. So this V we got, that is 1 volt. This we can show in the next page. So this potential came out to be 1 volt. And the same potential will be going here, right? So what do you understand by that? 3 minus 1 by R is equals to 100 microampere. Say yes or no? Because there is 0 ampere current here, 0 ampere current here, so 0 ampere current will be coming from here. So 3 minus 1, that means potential drop is 2. 2 by R is equals to 100 microampere. So what is the value of R? That is 20 kilo ohm. The value of R is 20 kilo ohm. That is our first answer. Well and good. Very good. Okay. Now they are asking what should be the minimum value of V naught such that M2 is working in saturation region. So what should be the minimum value of V naught for saturation region? VDS should be equals to VGS minus VT. What is VDS? That is V naught. What is VGS? That is 1 minus VT is 0.7. So V naught value should be 0.3. So what is the answer? V naught is 0.3 volt. What did you understand here? You understood that you have to make this, if you are making this circuit, you have to adjust V naught such that it is 0.3 volts so that it is working in saturation region. Now both are in saturation region, both have the same VGS, that means it is in current mirror. So 100 microampere current here, 100 microampere current here. By that you can get to know the value of R as well. So this was a very easy question. You could have solved it very easily, right? V value we find out, from that we could find out the value of R and V naught. Well and good. Okay, let's move on to our next concept. We will be building multiple current sources using current mirror. Multiple current sources. Here what did we do? We found out only one current source. I out. Only one current source we have made. We can make multiple current sources. How we will do it? So this is our VDD. We already have a golden current source, that is I naught. Now from this golden current source, I got to know there will be some circuitry here. Forget about that. This was M1, this was M2. So here what was my I copy 1? This was the current that I was getting, which was I copy 1. So my I copy 1 was, better I should write what here. I copy 1 was proportional to the W by L ratios. W by L ratio of M2 divided by W by L ratio of M1 into I naught. This was the I copy 1. Now what I can do, I will make one more MOS here. Similar thing I am doing. Okay, this is M3. I have to feed some voltage here, right? I have to feed some voltage here. That voltage will be this potential only. Simply this potential. I am feeding this potential only. Similarly, I can add more transistors. This will be my I copy 2. Similarly, I can add more transistor. Let's assume I add M3. the same voltage I am applying it here as well. So I am giving the same bias to this one as well. Bias means DC voltage. I am giving the same bias to this one as well. So if this is having V potential, if VGS value is V here, then this is also having VGS value. Now this is 0, this is V. So V is traveling here and V will reach here. So basically, again the potential is V. This is 0, this is V. So V is traveling, will reach here. So this is again V. So all are having V potential, and we make sure that all the transistors are working in saturation region. All transistors are in sat. We have to make sure this, that all transistors are working in saturation region. So all are working in saturation region, all are having the same potential. So basically the current will be copied, right? This will be I copy 3. So the current will be proportional to the W by L ratio. That's it. So I copy 2 would be what? Better write it here. What will be your I copy 2? That would be, if this is M2, this should be M3 and this should be M4. So W by L of M3 divided by W by L of M1 into I naught. This will be your I copy 2. And what about I copy 3? I copy 3 also you can write W by L of M4 divided by W by L of M1 into I naught. Say yes or no, right? So this is the circuit. Now this circuit sometimes is shown in a different manner. So I will add a page. So here I will write other way of showing the same circuit. Other way of showing the same circuit. Same circuit. So sometimes in the questions, this particular circuit that is shown here, this particular circuit, it's shown something like this. Let's copy this circuit first. So these supplies will be gone. They will not make the connection like this. Instead, what they will do, they will make a line like this, like this. They will make a line like this. Okay. Let's make a clearer structure. They will make a line like this. Here also they will make a line like this. What do they mean by that? That this node is connected to this node and this node is connected to this node. So all these nodes are connected. So the same circuit is shown like this. Are you getting this point? This is M2, this is M3. So in the examination, if you see these kind of circuit, what will you understand? You will understand this, that this potential is connected here, again this potential is connected here. So all the potential are common. That means this V potential is here as well. This V potential is here as well. This V potential is here as well. It doesn't mean that they connected a wire like this. They connected a wire like this. In the previous question that we have shown, they are connecting the wire like this, but shown like this. Okay, this will be your I copy 1. And this will be your I copy 2. This will be your I copy 2. So in the same way it is shown, and these equation will be the same. Nothing different will be there. Are you getting this point? So this is the same way of showing the other way of showing the same circuit, right? Let's see what we are going to check. So this is a question which we will be solving now. Okay, so let's solve this question. Actually someone came in the room, so I had to stop the video. So yeah, let's solve this question now. You have to make a common source amplifier using NMOS. So common source amplifier that will be made using NMOS with a 100 microampere current source in load. Okay, till now this is the question. 100 microampere current source in load. 100 microampere current source in load. This is the common source amplifier. Load will be at output. So this is the 100 microampere current source. Now this 100 microampere current source, from where you will be getting this? They are saying that you have a reference current source of 200 microampere. So from 200 microampere, you need to make 100 microampere. This is your task. Your task is to make this current source. How will you make from this 200 microampere current source? So that we will do. Okay. And what else they are giving? They are saying that you have only one supply VDD. You have only one supply. Here I cannot apply my input like this. That this is my small signal input Vin plus VGG. I cannot apply like this. Why so? Because I don't have VGG. I have only one supply. So if there is only one supply, how do you bias it? We have already seen it, right, in MOSFET amplifier. This is how we bias it. You have only one supply, that is VDD, R2, R1, and here I will apply my small signal input, that is my Vin. What else they are saying? Your small signal input Vs has an internal resistance Rs. So this my small signal input is something like this. It is having Vs and it is having Rs. So this is how I will apply my small signal input. Are you getting this point? This is the coupling capacitor. So when you do the DC analysis, only this will be in action. And when you do the AC analysis, this will come in action and there will be no use of this R1 and R2. Are you getting this point? Well and good. And now after designing the complete circuit, you have to find the small signal voltage gain. Now this is not the final design. Why it is not the final design? Because you have to design this 100 microampere current source. So how will you design that? Using current mirror circuit. Are you getting this point? What did they ask you to design? A common source amplifier with the 100 microampere current source in load. That's it. Then they said that you have only VDD. Okay, only VDD I am having. Then I have to bias it. How will I bias it? By using potential divider. R2 by R1. Resistor divider or potential divider using R2 and R1. I have to apply small signal input as well. Small signal input is having RS resistance. So Vs, RS, then there is coupling capacitor. So this is my design. This is not the final design because I have to make this 100 microampere current source as well. So now my next task would be what? What is my next task? That is designing 100 microampere current source from 200 microampere reference current. Now, where is your current source going? Your current source is going from VDD to some node. Say yes or no. It is going from VDD to some node. So if it is going from VDD to some node, so what we will have to use? Top to some node, we will use PMOS. You cannot use NMOS. We will use PMOS because it is going from VDD to some node. Top to some node. Top P for PMOS. So we are designing a 100 microampere current source from 200 microampere reference current. So you are having a 200 microampere reference current. 200 microampere reference current. This is what you are having. You will pass it through a PMOS, which is a diode connected transistor. So you are passing it through a PMOS. You have only one supply, that is VDD. And then one more PMOS will be there. You have only one supply. Source should be at higher potential. And here there will be some circuitry that we have already seen. So this is the 200 microampere current source which is flowing in this MOS as well. Let's just call this has W by L ratio. If this has some W by L ratio, what should be the W by L ratio of this transistor? It should be half of this. Are you agreeing to my point? Because if this is having 200 microampere current, and then if this is having half of W by L, then it will be having 100 microampere current. Are you understanding this point or not? So what was the question? You have to, these specs are given, you have to design the circuit. We started designing the circuit. We made this much of circuit, then we got to know we have to design a 100 microampere current source from 200 microampere reference current. This is the 200 microampere reference current we are having. We also got to know we have to design the current source such that it is going from supply to some node, supply to node, top to node, top P. That means we have to use PMOS. So we are using PMOS, 200 microampere current that is flowing through W by L. Then half of W by L will have 100 microampere current. So this is the current source that we have made. So this was our next task. So what will be your final design? Final design. So this is the final design I am having. This is 200 microampere current source. Here both are having the same VSG. Both are having the same VSG. And yeah, I have to write one more thing. Making sure that this transistor is working in fact. You have to make sure that this transistor is working in saturation region. Okay. This is, let's call this transistor as M3, this transistor as M2. Now this 100 microampere current source is fed to a common source amplifier. This is the V note we were having. Also, by using this VDD supply and a potential divider, I was getting my DC bias. This was R1, this was R2. This was the DC bias I was getting, and then I had my small signal source here. So this is my final design. I am done with my final design. I used only one VDD. I used only one supply. I had the resistance R1, R2. I got the bias from there. These are the transistor I am having. Let's call this transistor M1. I will adjust VDD R1, R2 such that all transistors are working in saturation. All transistors should be working in saturation. Why these two should be working in saturation? Because this is current mirror. And why this should be working in saturation region? Because you are using it as an amplifier. So all transistors are working in saturation region. This is having 200 microampere current, and what is the other relation? W by L of 3 is 2 times of W by L of 2, right? This is doubled. This is doubled. M3 is doubled. So this is half, right? So W by L of 2 is half of W by L of 3. So here there is 200 microampere current. So this will be having 100 microampere current. So this is our final design. Now what did they ask? This is not the final answer. They asked to, after designing the circuit, find the small signal voltage gain. Now you have to find the small signal voltage gain. So how you will find it? This is a very, very important concept. Watch it carefully. So I will find the small signal voltage gain now. So for finding the small signal voltage gain, what do we do? This supply will be shorted. So this will be shorted. What will happen to this current source? This will be open circuited. This current source will be open circuited. This circuit will be reduced something like this. Say yes or no. Are you agreeing to my point? This is M3. So from source to drain, you are having a R0 resistance. This is M3, so it will be having a R0 3 resistance. Say yes or no. R0 3 resistance, right? Forget about this 100 microampere. This VDD will also be shorted. This will also be shorted. This is having a R0 2 resistance. What about this? This VDD will be gone and R1 R2 will come in parallel. So better we make it like this. What will happen? This is Vs, this is Rs, R1 and R2 will come in parallel. R1 parallel R2 will be connected like this. Say yes or no. Are you agreeing to my point? What will happen to this circuitry? This is the task. What will happen to this much of circuitry? Because one thing I know, that from V0 to ground, from V0 to ground, from this V0 to ground, I see R0 1. From V0 to ground, I see R0 1. From V0 to ground, I see this MOS. And from V0 to ground, I see this much of circuitry. What will happen to this circuitry? Tell me. Let's assume there is V potential here. There is V potential here. So what I can say? From V to ground, I see R0 3. And from V to ground, I see 1 by GM3. Say yes or no. I told you, if there is this arrow, that means there is 1 by GM. Or how you can say, if this is V potential, if this is V potential, then how much current is there in this MOS? GMV. GMV. Will there be any current? No. Will there be any current? No. So will there be any current? No. So this V potential is, this M3 is having GMV current. So this V potential will be coming here as well, right? So from V potential, what do you see? From V potential, there is R0 3 current. Sorry, from V potential, there is V by R0 3, V by R0 3 current, and from this V potential, there is GM3V current. This is GM3V current. So what is the impedance you can say? R0 3 parallel with 1 by GM3. Say yes or no. Let me show you the circuit once again. What is the circuit? This is the circuit. These are shorted. This is also shorted. Here there is R0. And this is potential V. This potential V is carrying here as well. If this is V potential, that means here there is GMV current. Forget about this R0. Let's call it R0. You need to find the impedance from here. You need to find the impedance from here. So let's just assume if this is V potential, then what is the current here? That is I. So if this is V potential, this is the current I. So this I current would be equals to, there is no current here, there is no current here. Just a second. Yeah. So what I was saying, so from V to ground you see GMV current, from V to here you see V by R02 current. Right? So V by R02 plus GMV R02 or whatever it is R0, V by R0 plus GMV is equals to I. So what is the resistance you see? 1 by GM parallel with R0. Or you can directly say, from V to ground I see 1 by GM, from V to ground I see R0 3. So this much of circuitry, this much of circuitry will be replaced by simple resistance. This much of circuitry here will be replaced by simple resistance. From V to ground, what do you see? 1 by GM3 parallel with R0 3. Now, this is the circuit. 1 by GM parallel with R0 3. Now, this potential is being fed here. Now, this is the same, right? You are checking from V0. You are checking from the point of view of V0. Because your final target is from V0 to ground, what do you see? This is your final target. Okay. Now, this much of circuitry is replaced with a single resistance, that is 1 by GM3 parallel with R0 3. Now, how much current is this will have? Because here there is 0 ampere current. So, how much current this resistance will have? 0 ampere current only. This will also have 0 ampere current. This is ground, that means, if, and this resistance is having 0 ampere current. So, that means this voltage will be 0 volt. Are you agreeing to this? 0 ampere current is flowing. So, this potential will also be 0 volt. So, basically, this potential, this will be replaced with ground only. Yes or no? Here there is 0 ampere current, right? Also, this is also 0 ampere current. So, this will be replaced with ground. Here VSG is gone. If VSG is gone, that means there is 0 ampere current. So basically this much of complete circuit is replaced with single resistance R02. Say yes or no. Did you understand? This configuration was replaced with resistance 1 by GM3 parallel with R03. Then I got to know that this became grounded because there was 0 ampere current here, so this node would become grounded. If this is grounded, that means VSG is gone. If VSG is gone, that means MOS is having 0 ampere current. If MOS is having 0 ampere current, so from V0 to ground I see only R02. Say yes or no. So from V0 to ground I see R02, from V0 to ground I see here R01. Right? So what is the equivalent? Now what is the final equivalent? This is my Vs, Rs, R1 parallel R2. This is Rs, this is Vs. This is V0. So from V0 to ground, I see R01. From V0 to ground, I see R02. Now, whatever the potential that to get here into GM1 will be the current flowing. So then you can write down the gain. We have seen it in common source amplifier, so no worries about that. This was our one, this was our second, this was the final circuitry. So I hope you are understanding it. What will be the gain? Now I will directly write down the gain. You should be comfortable with this. What will be the gain? V0 by Vs. That would be GM1 into R minus sign certainly will be there because this is common source amplifier. R01, R02 into R1 parallel R2 upon Rs plus R1 parallel R2. Say yes or no. This is V0 by Vs. Are you agreeing to my point? This gain you can write. First write down the potential here, then the current here would be GMV. GM1V. The same current is flowing through R0 or this final output impedance. That current would be GMV. That current is flowing through V0. So what will be your V0? V0 would be GM1 into R01 parallel with R02 and minus sign. And what is the value of V? Value of V is R1 parallel R2 upon R1 parallel R2 plus Rs. So from there you could get this final answer V0 by Vs, that is this. So this was the first method from where you could find the small signal voltage gain. Now what is the other method? Here I know that this is a 200 microampere current source and this current source is copied into 100 microampere, right? So I can replace this much of circuitry with a simple current source, but that has some output impedance. This much of circuitry can be replaced with a simple current source that has the output impedance of M2. The output impedance of this side will not matter. Why? Because whatever the impedance we are having here, that will be going towards 0 only. Whatever the impedance we are having here, that is going towards 0 only. So only the impedance of this side is mattering. Impedance of this side is matters. Only impedance of this side matters. That's it. So the side which is connected to the M1 MOSFET, only the impedance of that side is mattering. So whatever the current that is being pushed into M1, whatever the current that is being pushed into M1, only the impedance of that side matters. That's it. So what is our method 2 now? Method 2. So simply we have a 100 microampere current source here. Now how much output impedance this 100 microampere current source is having? From this particular node you will see that is R02, right? So you will make that this is the 100 microampere current source you are having, which is having a resistance of R02, and then you are having a common source amplifier. This is Vs, this is Rs, this is V0, and this is grounded. And if you are doing the small signal analysis, then this 100 microampere current source will also be gone. Why it will be gone? Because this is a DC current source. What do you see? From V0 to ground, you only see R0 2 resistance, right? And from here you see R0 1 resistance. So simply your circuit is replaced with, from V0 to ground, R1 parallel with R0 2, right? So here I will just make the circuit once again. Here I will make the 100 microampere current source so that students will be comfortable. This is VDD and this R0 2 is connected like this. Then if you do the small signal analysis, this will be gone. And here we are having R1 parallel R2. Or better I should make, here I am making the complete circuit only, not just the small signal. This is R1, this is R2, this is VDD, this is RS, this is V, this is VS, this is capacitor C. So what will be the final circuit after the small signal analysis? This would be RS, this would be R1 parallel R2, and here you are having this MOS, and from V0 to ground you are having R0 1 parallel with R0 2, and this is your VS. That's it. This was your M1. So this is the small signal analysis. Did you get to know? So for gate aspirant, what will be the question? For the gate aspirant, this circuit will be given. In the examination, they will not ask you to design a circuit. But if you learn to design a circuit, it will be very helpful for you. Because just by seeing the circuit, you will get to know, okay, they have designed it in a way that 100 microampere current is acting as a load for common source amplifier. If I had directly given this circuit to you, okay, and I had asked you to find the small signal voltage gain, then you wouldn't be learning anything. You would be only learning how to solve a particular problem. But what we are doing in the complete course, first we are designing something and then we are learning how to solve it. Are you getting this point? This is my objective of teaching this course. First we design, and once you see the question, you should be knowing what they actually want to ask. So if this question was in front of you and they ask you the small signal gain, what you would understand? That they are using a 100 microampere current source as a load. Now this 100 microampere current source will have the output impedance similar to what M2 is having. So from here, what is the output impedance do you see? That is R02. So directly you will make R02. Nothing you will see. You will not even see here because the current is copied here. That's it. So you will make R02. Then you will make this M1 and directly you will write down the final gain. So this was the objective. That's why we are spending so much of time, so that in the examination you have to spend the minimum time. And toughest of toughest question you will be able to solve. Say yes or no. Let's move on to our next question. Next question you will be solving it on your own. So this is the next question. You have to design a common drain amplifier. Common drain amplifier will be made using NMOS. Design a common drain amplifier which will be made using NMOS with a 100 microampere current source in load. So you have to design a common drain amplifier. They are not talking about the supply, so we have different supplies now. So common drain amplifier using NMOS. This is the common drain. In common drain, you apply the input here, you get the output here. Apply the input at gate, get the output as a source. 100 microampere current source in load. In load, you are using 100 microampere current source. This 100 microampere current source, you have a reference current source of 200 microampere. From 200 microampere, you need to make 100 microampere current source. But what is the condition? That all the transistors are having the same W by L ratios. This is the condition now. Here, what did you do? That sir, here I am having W by L ratio of W by L, and here my W by L ratio is half of the previous one. But now they have said that all the transistors are having the same W by L ratio. So what you will do now? This is the question. Think about it and tell me. Use your complete brain. Think about it. If you are able to think, then it's very good. If you are not able to think, No worries, even I was not able to think about it in the first chance. Okay, so no worries if you are not able to think. If you are able to think, that is very good. So what this Vin would be, let's first write it. It will be small signal Vin plus VGG. But they are not talking about supply and anything now. Here I talked about supply and everything. So here I have eradicated all those things. So now our task is to design a 100 microampere current source from 200 microampere golden source, but W by L ratio is same. So what you will do? So my task is now designing 100 microampere current source. How will you design it? You have a 200 microampere current source. One thing I know, that this current will be copied. One thing I know, the current will be copied, right? But the current that is going to be copied, that has to be 100 microampere, because W by L ratio is same. What is the copied current? Copied current is W by L of someone divided by W by L of the other one into the current. Now W by L is same. So copied current will be the same as whatever the current that you are having. But the current that you are having is 200 microampere. So you need to get 100 microampere out of it. Say yes or no. How you can get 100 microampere from 200 microampere current? If there is I current flowing, I pass it through two equal resistance. This is resistance R, this is resistance R, this is I current. What will be the current in this one? I by 2. What will be the current in this one? I by 2. The same thing we are going to do here. 200 microampere current you are having. I am going to, okay. Now secondly, what you will use for making a current source now? NMOS or PMOS? For making a current source, what you are going to use? NMOS or PMOS? We are going to use NMOS. Why so? Because we are going from some node to ground, node N, node to ground. That means I am going to use NMOS. Okay, better, I will make a better circuit. Basically, this 200 microampere current should be divided into two parts. 200 microampere current should be divided into two parts, and then that current will be copied here. This current will be copied here. And here there will be the MOSFET amplifier. Here that will be the circuit. This current will be copied. टेढ़ा हो गया भाई. You have to divide the current. How will you divide the current? This should be looking here like this. This should be diode connected as well. Say diode connected, and the same kind of transistor I can add here. That's it. This is your VDD. VDD 200 microampere current is coming. Now that current will be divided into two transistors. Both are having the same W by L, so both will have the same current, 100 micro. This will also have the 100 microampere current. Now this current, this is having V potential. If this is having 100 microampere current, this is having V potential. That means this will also have V potential. Now this same V potential will be fed to this. All are having the same V potential. All are in the saturation region. That means all will have the same current. That this will also have the same 100 microampere current. Say yes or no. Did you understand this question or not? You had 200 microampere. You need to get 100 microampere current out of it. You need to divide that current. I divided that current into two diode connected MOS. Both are in saturation region. Both are in saturation region. Both have the same W by L ratio. That means both will have the same current. So 200 will be divided into two parts. 100, 100. Say yes or no. Right? 100, 100. Both current are divided. If 100 microampere current is flowing, that means there will be a voltage developed V across them. Both of them will have the same voltage. Why both of them will have the same voltage? Because both are having the same current. That's why both of them will have the same voltage. Or better, I should short circuit their voltages. Or it is already shorted actually. If this is 0, this is V, then this will be V only. Both have the same voltage already. So both have same VGS, both have same WIL, both have same VT, everything is same. That means both will have the same current. So 200 microampere current will be divided into two parts. That will be 100 microampere and 100 microampere. Are you getting this point? So both are having 100 microampere current. Because of this 100 microampere current, some voltage is developed. That is V. The same voltage is fed to the other transistor. Now I am making sure that this transistor is working in saturation region. I will make sure by the supply, I will make sure that this transistor is working in saturation region. So that is having 100 microampere current, which is acting as a load for a common drain amplifier. So what will be my final design? So in my final design, I will copy this circuit only. Array, wow. This current source I have made. So simply I need to use a common drain amplifier here. This was VDD. This is V in. And this is my V out. If this transistor is M, all the transistor that you are having is having same W by L. So all the transistors are identical. All what you are having is NMOS, all transistors are identical. Tell me the small signal voltage gain for this. Write down your final answer and then match it. What is your final answer? GM R naught upon 2 plus GM R naught. If you are getting this answer, just close this video and move to the next video. If you did not get this answer, then watch the solution. If you are getting this answer, forget it. You are great. You have understood everything from this lecture. Just move to the next lecture. If you are not getting it, then watch the video. यही आएगा ना यार कहीं GMR नोट यही आएगा. Okay. What did I tell you? This will have 100 microampere current. This will also have 100 microampere current. What they will act as? They will act as a current source, and their impedance doesn't even matter. Also, what we can do, first let's solve it by the conventional method. What is the conventional method? I need to look the impedance from here. What is the impedance do I see from here? So I need to look that impedance. So if this is voltage V, this will also be voltage V. So here from V to ground I see 1 by GM. From V to ground I see R0. From V to ground I see R0. From V to ground I see 1 by GM. So from V to ground what do I see? 1 by GM parallel with R0, parallel with 1 by GM, parallel with R0. Say yes or no. From V to ground I see 1 by GM. From V to ground I see R0. From this V to ground I see 1 by GM. From V to ground I see R0. From V to ground 1 by GM. From V to ground R0. So this much of region will be replaced by 1 by GM parallel with R0, parallel with 1 by GM, parallel with R0. Say yes or no. Let's do the small signal analysis of this. This is the final design. Now we are going to do the small signal analysis. Small signal analysis. All transistors are already working in saturation, so forget about it. This is 200 microampere, which will be gone. From V to ground 1 by GM parallel with R0, parallel with 1 by GM, parallel with R0. So this much of circuitry will be replaced by, from V to ground, you are having 1 by GM parallel with R0, parallel with 1 by GM, parallel with R0. Whatever the impedance you are having here, does that matter? No, because this is 0 ampere current. If this is 0 ampere current, this will also be 0 ampere current. That means this node will be grounded only. And if this node is grounded, that means VGS is gone. And if VGS is gone, so from V0 to ground, you only see R0 resistance. That's it. Are you getting this point or not? And this is also grounded in small signal analysis. And in this, in place of V in, I will write small signal V in. So from V0 to ground I see R0, from V0 to ground here also I see R0, because the same current, 0 ampere current is flowing here. The resistance is having 0 volt drop. This is 0. This is 0. This is also 0. So VGS is gone. So complete 0 it is. So from V0 to ground I see only R0. From V0 to ground I see only R0. So here, this is my V in. V0 to ground, I see R0 parallel with R0. That would be R0 by 2. And this is grounded. What will be my gain now? This is 1 by GM here. This is 1 by GM. So what will be the gain? V0 by V in. That would be R0 by 2 upon R0 by 2 upon 1 by GM plus R0 by 2. So what we will get? GM R0 upon 2 plus GM R0 V0 by V in. This is the final answer. So always remember one thing. No matter how many current mirrors do you use here, only the current mirror will matter which is acting as a load. That's it. Only the current source which is acting as a load, that will matter only. These will not matter, because everything which we are having here, that will be replaced by a single resistance. So this is replaced by a single resistance, and here there is 0 ampere current. So this resistance will also have the 0 ampere current. So here that voltage drop will also be 0. If voltage drop is 0, that means there is no use of this. Now VSG is also gone. If VSG is gone, what does that mean? If VGS or VSG is gone, that means this M will be replaced with open circuited. Whatever the output resistance it is having, that will come into action. So this M was having R02 output impedance. So only R02 output impedance will come in action. Say yes or no. Are you able to understand the complete concept? I hope you are able to understand the complete concept. So this is the current mirror that should be taught in the gate field, but it is not taught in this manner. In the small signal analysis should be taught for this current mirror as well. And I will show you the questions which have been asked in the previous gate examination from the small signal analysis of current mirror. So what is the conclusion that we got to know in current mirror? No matter whatever the circuitry you are having here, the final resistance would matter, that is here. So I will write down a conclusion. What is the conclusion? Let's just assume this is a VDD. From here you are having a current source of some ID. Then there will be a lot of diode connected transistor. There can be a lot of diode connected transistor. One, then more will be there. Two, this is also diode connected. There will be more like that. Then there will be this final one. The voltage from this will be fed to the final transistor here, and above that you will be having some circuitry, some amp you will be having. So what do you see from here? What do you see from here? So from here, from V0, what do I see? From V0, at the above side I will see an amp. And here I will see a current source, whatever the current I get, a current source, and the output impedance of this. That's it. What is the output impedance of M? So R0 of, let's call this M dash. So R0 of this M dash. That's it. This is the conclusion. Are you getting this point? No matter whatever you are having, all will be replaced with a single resistance. And if this is replaced with a single resistance, then 0 ampere current would make the potential here 0. Then VGS will be gone, and if VGS is gone, then only one resistance I see. That is it. I hope you have understood the concept of current mirror. In the next video, we will see very interesting question on current mirror circuit and cascade amplifier. So next will be an assignment which you will be solving. Okay, so that will be assignment 9, I guess, or 10, I don't know. I will check it. Assignment 9 as far as I remember. So next we will see assignment 9. Okay, thank you.